Look up at the constellation Orion, and you'll easily spot its shoulder. That bright reddish anchor is Betelgeuse. It's a highly volatile, unstable red supergiant. To grasp its physical size, you have to look past our own solar system. You could squeeze over 1 billion of our suns inside Betelgeuse. It is a pulsating, shifting mass that is rapidly pushing towards its final fusion cycles before it inevitably detonates. In 2019, astronomers caught it doing exactly that. During the Great Dimming, the star blasted an enormous chunk of seething plasma deep into space. The material cooled into dust and blocked the star's own light from our telescopes, proving how unstable the surface really is. This historical map shows how humans tracked the Orion constellation over time. Looking at records from ancient Greek astronomers, we can see that over the centuries, humans have watched Betelgeuse transition from a pale yellow star into the deep red supergiant we observe today. Right now, it sits about 600 light-years away from us. When it does go supernova, it will put on a spectacular light show in our sky. But at that distance, the radiation will safely dissipate long before it ever touches Earth's atmosphere. Space is filled with dying stars. If we strip away that 600 light-year buffer and move this massive star closer to home, the physics of a supernova shift from a beautiful light show into a lethal threat. Let's run the simulation. We'll set the first simulation distance to 160 light-years away. If Betelgeuse exploded from here, the blast would light up our night sky with the intensity of a full moon, remaining completely visible even in broad daylight. This visualization shows the vulnerable gaps in Earth's ozone layer. At 160 light-years, the immediate danger isn't heat, it's X-rays. The explosion would shower our planet in radiation, actively punching holes through this thin atmospheric shield that usually acts as our primary defense against the sun's harsh UV rays. Down on the surface, you would get severe sunburns after just minutes outside. Global auroras would light up skies everywhere, and the elevated radiation levels would cause a widespread spike in DNA mutations and skin cancer. Next, we move the star to 50 light-years away. At this proximity, the sheer volume of high-energy radiation completely overwhelms our atmospheric defenses, entirely shredding whatever is left of the ozone layer. This photograph shows a thriving coral reef, which, along with ocean phytoplankton, would be the first casualties. Since these microscopic plants and reef structures form the base of the global food web, their destruction triggers a total collapse of marine ecosystems that rapidly ripples upward to apex predators. On land, the atmosphere quickly becomes swamped with a thick smog of nitrous oxide as the climate destabilizes. At 50 light-years, we reach a terminal threshold. A supernova at this distance strips the planet of its biological life, causing a mass extinction event without a single physical flame ever crossing the solar system to touch the Earth. For the final parameter, we drop the distance to 0. We're removing our sun and putting Betelgeuse directly in the center of our solar system. This vector map traces out the inner solar system. Because Betelgeuse is up to 1,000 times larger in diameter than our sun, its surface stretches outward for over 4 astronomical units. That expanding red boundary instantly consumes the orbital paths of Mercury, Venus, Earth, and even Mars. There is no new orbit for Earth. As that boundary passes us, the planet is completely engulfed in a 3,200-degree stellar inferno, incinerating the surface and dissolving the globe into ash before the star even has a chance to explode. This puts Jupiter on the front lines. The massive gas giant depicted here would survive the initial expansion, but transform into a hot Jupiter. Instead of a normal orbit, it would now circle this supergiant every 12 years, boiling as its hydrogen and helium are constantly cooked by the star. Even the coldest reaches of the solar system aren't safe from the heat. The ice inside Saturn's rings would vaporize into space. Looking at Saturn's moon Titan in this hazy image, its dense atmosphere would puff up, turning its usual methane rain into liquid water. There is also a chaotic variable here. Scientists recently discovered that Betelgeuse has a binary companion star, roughly the size of our Sun, orbiting at a distance of about 4 astronomical units. If we teleported the whole system, that companion would be tearing directly through Saturn's orbital path. Placing Betelgeuse at our center effectively erases the solar system's original architecture. The star's immense luminosity pushes the new habitable zone over 300 astronomical units away, relocating any chance for liquid water out into the deep freeze of the Kuiper Belt. Even if life somehow migrated out to the edge of the solar system, the clock runs out quickly. Betelgeuse has already exhausted its supply of hydrogen and helium fuel, forcing it to burn heavier elements to keep gravity at bay. This diagram shows the star's mechanical breaking point. Once the core fills with iron, fusion stops entirely. Without outward energy, gravity takes over. The immense mass plummets inward, violently crushing the core, then instantly bounces off it, projecting a shockwave that shreds the star apart. The math on this detonation is extreme. In just a few seconds, the exploding supergiant releases more concentrated energy than our sun will produce over its entire 10 billion-year lifespan. After the blast clears, the solar system as we know it is gone. Here you can see what it's replaced with, an expansive, glowing nebula of gas and dust, stretching across the space where planets used to orbit. This detonation is the only event in the universe powerful enough to forge heavy elements like carbon, gold, and iron, and scatter them across the galaxy. These extreme cosmic detonations are strictly required to create the iron pumping through our blood and the basic building blocks of life on Earth. We owe our existence to dying stars, but our only real defense against their raw, destructive power is the unimaginably vast, isolating distance of the universe itself.